Okay, we're back for another day. Stellar spectroscopy, aka mostly spectroscopy up to this point, the fundamentals thereof. And we're eventually going to get into the stellar atmosphere. That's our next segment. But in the meantime, we want to talk about the gas. So we've talked about all the way back in the beginning, optical depth, cross sections, line formations, and all the structure of the atom. And now I think if you went to NIST, some of you clearly already have and know how to do that, you could now interpret those line lists quite well in terms of the Russell-Saunders notation and things like that, and what the J's are, what the G's are, what the A's are in terms of the Einstein A's, and how you obtain the damping coefficient. But now we're into the gas, and we've defined the total number density as the nuclear number density plus the electron density. And we've defined the nuclear density as the sum of the densities over all species, over all ionization stages, over all excitation states. Nijk, the number density of species K in ionization stage J in excitation state I. Okay, you sum all of those together, what do you get? Njk. You sum all the Njk, that's the number of all species, that's the number of species K in ionization stage J, which accounts for all their excitation states. If you sum the Njk over all J, then you get the Nk, the number density of species K, which is the sum of them over all their ionization stages and their excitation states. And then if you sum all the Nk, you get N nuclei. Then if you know the electron density and you know the nuclei density, you get the total density here. We said the total density is related through the pressure times NKT. So if you know T and you know P, you can get N. If you know N, you know what the sum of those are. Okay? If you get NE from knowing that, and it's a circular solution. Okay? Given the pressure and temperature, you can use this information to calculate every one of these. Okay? And we defined FJK as Njk over Nk. Okay? So in other words, what's the number density of species K in ionization stage J relative to the number density of all of species K? Okay. So we know that we have density conservation. So we know that if you've got some Njk that's been ionized, say twice, then it donates J-1 electrons, and so its contribution to the number density of electrons is J-1 Njk. Right? And we also defined the abundance fraction as N of K over all N nuclei. So if you know that abundance pattern of your gas, and you know the total density N, which means you have to know the pressure and the temperature, then you can use these equations. You solve this equation for Ne. Once you know Ne and you know total N, you can calculate this N. Once you know that N, if you know this number already, you can calculate all the n sub k. Once you know the n sub k, you can, from the ionization fractions, which is part of the solution to this, you can calculate the njk, and you got everything. Should I do that one more time? How you do that? Okay. If you know the pressure and temperature, you get the total N. This is known. If you know the abundance pattern, alpha K, which you read off some abundance table, there you know that. Armed with those, you solve this equation. I have to teach you how to calculate this, what physics goes into calculating that ionization fraction. If you know how to calculate that given your conditions of your gas, you can solve this equation. You get an equilibrium NE solution for this, okay? But that also tells you the FJK, all right? Now, first, since you've solved for the electron density, you can solve this equation, knowing N, knowing Ne, for the nuclei number density. From the nuclei number density and the AK that you know, you can calculate the number density of all species. From the number density of each species and the ionization fraction, which you got out from the equilibrium solution, you can calculate all the NJK. So you basically can back out and solve for everything in the equilibrium solution. This will become more real to you when I give you a homework problem. Okay. All right. What I need to do is teach you how to calculate this. Okay? We're going to get there, but I might get to it toward the end of today. In fact, that's what my plan is. Okay, but what I want to do is I want to go back to this pressure, and I want to talk to you about mean molecular weights today. Okay? Excuse me. And mean molecular weights come about because in the end, a lot of people like to talk not about number densities, but they like to talk about mass densities. If you are doing all of your calculations in number densities, you don't have to worry about the masses of the different ions and how there's different, each different ion from a species, each species has a different mass. If you're talking about mass densities, you have to account for the fact that you have a distribution of different species, and each of those species has a different mass. It's very much more complicated. Okay. So I want to remind you of a relationship that is that rho of the nuclei is equal to AK over XK MA times NK. Okay, where did that come about? It comes about because rho is equal to the mass times the number density. The mass is equal to the atomic number times the atomic mass unit. Why is there an XK there? Oh, this is XK, this is rho n. Okay? Rho of nuclei is the average mass of all the nuclei times the number density of all nuclei. Okay? All right. But if you want to turn this into K, you have to realize that rho K equals MK NK. MK is equal to AK MA NK. Okay? And then the difference, if you remember, XK is defined as rho K over rho nuclei. Okay? So rho xk times rho of all nuclei. Okay, so basically, you want to substitute that there. You've got xk rho n equals ak ma nk, so that now you get rho n equals ak over xk ma nk. All right. That's going to be very important pretty soon. You're like, oh my God. What have I showed you? What do you have to know? To do something like this, what do you have to know? You have to know basically this definition and the definition that mk equals ak times ma. Those are your two key points. From there, you can derive all these things. Those are the two key points. That the mass of species K is basically the atomic mass unit times its atomic mass number. That's easy, right? That you can remember. No problem. Bang. And the definition of the mass fraction, which is of species K, which is the mass density of species K divided by the mass density of all nuclei. From there, it's just algebra. All right, so it's not as complicated as it looks. All right, I just stupidly went through a very complicated algebraic definition to make it seem more complicated than it really is. All right. So what we're getting at is we know that P equals NKT. All right. So we're going to have, this is the total pressure, but we're going to have the pressure of the gas, which is equal to the P of the nuclei plus the P of the electrons. Okay, which is equal to N nuclei, KT, plus N electrons, KT. Everybody with me? Okay. This quantity is really equal to P nuclei plus P electrons plus P radiation. Okay. But sometimes we write these two as P gas. Okay. Well, that's fine and dandy, except for that, what if we want to do this not in number densities, but we want to do it in mass densities? Okay. Well, let's just for now, let's focus on P nuclei. Okay. It turns out that you can write this, and I'm just gonna, because you have basically rho K equals MK NK, you can write this as, hold on a second, oh, you also have rho N equals M bar M N nuclei. So we're going to be able to rewrite this. Okay, so let's do this. Forget that arrow, sorry. We're going to say that this, remember that n sub n is equal to the sum over all n sub k's. Does everybody agree with that? Okay. This is the sum of all species k. Total number. Okay, great. But from here, NK is rho k over mk. Okay, so how do you get the total pressure of the nuclei from this? And it turns out that the easiest way to do that is to redefine this in terms of something called the mean molecular weight. This is the definition right here. Okay. So what have we done? We said Mn is the sum of all the species K, but the number density of species K can be written as the mass density divided by the mass for that species K. Now we're going to say take this whole sum and set that equal to rho n over mu n ma. So what we're doing here basically, what is this numerator? When you sum over all K, it will give you back rho sub n, won't it? The numerator will give you back rho sub n, because rho sub n was the sum of all rho sub K. Okay, so I get that. This is m sub K. When we sum that up, what we're doing is we're saying we're going to write it as some kind of mean. Okay. So if you solve this equation for mu n, what do you get? Well, it's easier if we solve it for 1 over mu n because of that. So we just basically multiply by that, divide by that. We get ma over rho n. Sorry, it's supposed to be an equal sign there. Equals ma over rho n times the sine of rho k over mk. So that defines the mean molecular weight, or the inverse of it. So basically, you have to know the density of the entire nuclear pool, and you need to know the density of each of the individuals and their masses to calculate that. Well, folks, that's just not going to happen that way. So what I'm going to do then is I'm going to show you that you can simplify that. Okay. If you take the fact that rho k over mk is equal to rho n over ma times xk over ak. Again, what does that come about from? It comes from the fact that xk is defined as rho k over rho n, and that mk is defined as ak times mk. Okay? So if you apply these two things, okay, you can get, and I guess you need to know that rho k equals mk nk. All right. Oh, I got that right. I don't think you actually need to know that. All right. Anyway, from these two relationships, you can derive this. You've got the AK, you got the XK, you got the rho n, you got the rho k. All right. All right. So from this, you can put this in here, substitute that in there, and you end up with 1 over mu n is equal to the sum of xk over ak, or mu sub n equals the sum of xk over ak to the minus 1. And that, folks, you can calculate if you know the mass fractions. Okay? If you know the mass fractions of all your species, you know the atomic number of all your species. You take the ratio, you sum all of them over all k, you take the inverse of that, and bang, you've got mu sub n. Okay? So now what I'm saying is that you can calculate P sub n is equal to k over mu sub n ma rho sub n t. All you have to know is the mass fractions of each element. Okay? Well, I've taught you, if you're given a table of the abundances in log 12, I've taught you how to calculate the abundance fraction, and I've taught you how to calculate the mass fraction, and I've taught you how to transfer from abundance fractions to mass fractions, or from mass fractions to abundance fractions. Okay? So, what we're saying here is that if you want to write this pressure in terms of the nuclear mass density, you have to know the mean molecular weight. To get the mean molecular weight of the nuclei, all you need is the mass fractions or atomic weights, and you follow that equation. Okay? You're basically calculating this times some constants. Okay. Okay. Does it depend upon the ionization conditions? Do you see any J's in your subscripts? Can someone shake their head no? Yeah. Okay. So one of the things to develop some intuition is look and see what subscripts are there. If there's no J's, it doesn't depend upon ionization conditions. If it's only K's, it only depends upon the species that are present. I wish I'd done a better job of motivating this equation. Okay, but it's actually pullable out here. I believe this is rho k right here. So it's easy. It's possible to get out. So okay. So should I leave that here? I'm going to leave that over here. That's for the nuclei. That's for the nuclei. Only the nuclei. Not for the electrons. Okay? So how, that's the nuclei. That's this pressure. Okay? Nuclei, mean molecular weight of nuclei depending on the mass fractions of the species. What about electron pressure? Okay. Well, we're going to define, by definition, P sub E in terms of NEKT. Everybody with that? Okay. NE we're going to define this way, as to follow the form of this equation here. We're going to follow this form of this equation here and write it in terms of the nuclei density and a mean molecular weight. But this mean molecular weight is going to be that of electrons. So we're going to write it like this: K over mu sub E MA times rho of N T. Okay. So what we're doing with the pressure for the electrons component to the gas, to the entire pressure of the radiation plus gas, we're going to write it in the same form where we're going to use this form with the nuclei density, but we're going to write down something called mu sub e. Okay. So what do we get? Well, again, applying that xk equals rho k over rho n, and applying the fact that mk equals ak ma. All right. What we're going to find out then is we can put these together, and we use this relationship again. Whoops. Whoopsies. I'm looking at the wrong place. Damn it. Forget that. I'm looking at the wrong place in my notes. We're just going to solve this equation right here. Here's your k, here's your k, here's your t. We're just going to solve this equation here, and we're going to get Ne equals rho n over mu e ma. Okay? So we solve that for mu e, and we get rho n over ma times 1 over ne. Okay, there it is. If we know the entire nuclear density, mass density, we take away its mass, turn it into a number density by dividing by the atomic mass unit, and then we divide by the electron density, and we get the mean molecular weight. So if we want to write the electron pressure in terms of the nuclear density, we can do it this way. But we need Ne. Yes, ma'am?
So I guess I'm a little confused because in your notes you have the...
Yes. So, thank you for bringing that up. I forgot. Okay. When I taught this before, I wrote that as a rho sub e.
Yeah.
And then I calculated it. And then I realized later that that was actually not the way that it's actually done it as a standard way of approaching it. Okay? So, at this point, thank you for bringing it up.
Okay.
The typewritten notes, pages 62 and 63, and 64, 62 through 64, those have it using the method that I'm using today. In the end, it's 99% they're the same derivation, 99%, okay? But what I failed to realize when I taught this before in the past and wrote this hand notes was that technically this is defined in terms of rho n, not rho e. And that was my mistake. So my handwritten notes on this one should just, you should go to the typewritten notes or go to the lecture notes that you're getting today. Okay. All right, does anybody remember what Ne is?
Drew said it was 5.
Well, turns out that assuming you know the n sub k, that Ne can be written as this. Now, this was actually one of the equations I wrote down last time we met, but then I constrained it to the total density. But assuming you know the Nk and the Fjk, Ne is equal to this. Okay, so remember what we're doing here is this is actually the sum of all the Njk times j minus 1. Okay, so basically this is the number density conservation that each ionization state J donates j minus 1 electrons to the gas with the same density that the donor had, and then you sum over all of the different species and you get the total electron density contribution from them. I actually derived this equation for you last time we met, but then I took it further to constrain it to this equation and showed you the transcendental equation. But if you know the Nk and the Fjk, this is what Ne would be. Okay? All right. So, basically, you substitute that into here. Okay, and what do we get? U sub E is equal to sum over all k of xk over ak times the sum. How did I get there? I skipped a step and I apologize. What does NK equal? Okay. So you have an xk and n. All right. And rho n equals ma n n. Okay, so basically you can substitute here, all right, and you can get what I want. I want rho n over ma, so you can get nk equals xk times rho n is, this is rho n over ma. Okay, so you get rho n over ma equals nk over xk. I got something wrong here. This is where am I missing the a from? I used to know all this stuff so cold. What I got was nk. What did I derive? I got nk equaled xk over ak. Okay, how did I get that? From 6.14. Now you've got me curious how I got that. Oh yeah, page 58. I've derived these. Now I know I'm dying to see how I got it though. So bear with me for a second. Is this wrong? This is what I'm not sure of. Oh, that's what it is. Rho n is equal to ak xk times ma nk. So then you get this nk equals that. All right. So there you have it. Okay. And then from nk substitution, you get the xk over ak, but then you're multiplying this by 1 over ne, so that the rho n cancels with the rho n, the ma cancels with the ma. Pull it out of the sum, it cancels, and you're left with the sum of the xk over xk over ak. Whew. Okay, got it. Sorry about that. In the end, it's the boxed formula that you're going to end up using, if you use them at all. So it's a lot of algebra, but the point is now, forget the algebra. Hopefully it at least gave you an idea where these things come from. That's the important point to walk away with. So that we now can write the the pressures in terms of the nuclear density, and we can write the nuclear pressure in terms of the mean molecular weight, which only depends upon the mass fractions. And then we can write the electron mean molecular weight to get the electron pressure in terms of the nuclear density again, but it's equal to this summation here. You have to know the ionization conditions, and you have to know the mass fractions. Okay, so if you ever need to calculate these, you might be reading a paper and they say, we assume a mean molecular weight of such and such. It's giving you a clue about this. Or if they say we're assuming an electron mean molecular weight for a fully ionized gas, you should be able to go through and verify their number, for example.